So this is a review of the paper Kolmogorov Arnold Networks. This was published towards the end of May 2024. So the paper proposes an alternative to traditional multi-layer perceptrons, which is based on the Kolmogorov Arnold representation theorem. The main difference being learnable activation on edges instead of linear weights. So the nonlinearity is learnable here instead of being fixed activation functions in MLPs. So they observe that CANs outperform MLPs in terms of accuracy and interpretability. For accuracies much smaller, CANs can achieve comparable or better accuracy than much larger MLPs in data fitting and PDE solving. CANs also possess faster neural scaling laws than MLPs. For interpretability, CANs can actually be intuitively visualized, and we can easily interact with the activation functions personally. So since we're able to learn the activation function, we're able to see what exactly is the activation function that has been learned and how each input feature is being transformed to obtain the output, which allows us to see the relationship between the input feature and the output. And CANs are also shown to be useful collaborators, helping rediscover mathematical and physical laws and potentially discover new laws. Some drawbacks include slower training, the inability to be used for parallel computation, scalability, and overfitting. So comparing MLPs and CANs, we can see how MLP is based on the universal approximation theorem, whereas CAN is based on the Kolmogorov Arnold representation theorem. And of course, the MLP has fixed activation on the nodes, whereas CANs have learnable activation on edges. MLPs have linear weights on edges, whereas CANs do not have any linear weights, which are instead replaced by the univariate functions. These learnable univariate functions are parameterized as a spline, which are learnable 1D functions. And we have a fixed nonlinearity in MLPs, whereas a learnable nonlinearity in CANs. And the only multivariate function is the sum of these activations at the nodes. Some advantages of CANs are the higher accuracy with fewer parameters. The authors show an example where for PDE solving, partial differential equation solving, a 2-layer with 10 CAN is 100 times more accurate than a 4-layer with 100 MLP, whereas the parameters is much lower. For 2-layer with 10 it's just 20, and for a 4-layer with 100 it's 400. And so yeah, it's more efficient. Smaller CANs can outperform larger MLPs, which allows for much smaller computation graphs. And again, for interpretability, they can be visualized. The spline functions that we learn can be visualized, and this can help us in understanding the learned model. Symbolic relationships can be identified, and CANs take advantage of the intrinsically low dimensional representation of the function and are aligned with the symbolic functions. So splines are accurate for lower dimension functions. They are easy to adjust locally, and they're able to switch between different resolutions. However, splines have a serious cause of dimensionality problem because of their inability to exploit compositional structures. MLPs, on the other hand, suffer less from because of dimensionality, but they are less accurate in low dimensions. Now, CANs combines the strength of MLPs and splines, making them capable of learning both composition structures and univariate functions accurately. And now, this is the Kolmogorov Arnold representation theorem, which states that any multivariate continuous function on a bounded domain can be represented as a finite composition of continuous functions of a single variable and the binary operation of addition. Now, if there are n inputs, we can see how there is a summation over 2n plus 1 feature vectors. So if there are n inputs, there are 2n plus 1 nodes in the hidden layer. And finally, we get the output of the function that we are learning is the output. And CANs leverage this theorem to construct neural networks with just univariate functions and additions on top of that. So this approach simplifies the learning of complex functions by breaking them down into simpler competents, 2n plus 1 competents in this case. And but then these 1D functions can be non-smooth and even fractal, so they may not be actually learnable in practice. But then, of course, we assume that most functions in science and daily life are often smooth and have sparse compositional structures. and would be able to be represented using the Kolmogorov Arnold representation. And the authors assume that they take the general case of being able to use these representations to present or at least provide an accurate representation using these using this theorem. So using the Kolmogorov Arnold representation for neural networks is something that has already been studied, but then most of these prior works stick to the original 2-layer with 2n+1 networks, which uses this formula directly, which were limited in expressive power, and many of them were even before backpropagation. So this paper's contribution lies mainly in generalizing this network to arbitrary widths and depths. The study generalizes the network and allows it to have different set of layers, different size of layers, different shapes, and instead of just sticking to one hidden layer with 2n+1 nodes. So yeah, let's proceed. So can architecture, the nodes perform the summation. So these are two inputs. There are 2n+1 nodes in the hidden layer, and finally we get the output. So this is a representation of the direct representation theorem that we saw in the previous slide. So nodes perform the summation of the incoming signals, the activations from the previous layer, and then the edges have learnable activation functions modeled as B-splines. So this is what the B-splines look like, and they also propose grid extension for increased accuracy, which we'll take a look at a bit later. So again, activation functions are placed on the edges. They have the learnable coefficients are the local B-spline basis functions. So, but then to be able to build a neural network with this, we first need to define what a layer is, so that we can stack these layers one on top of the other to get deeper networks. Now, okay, a CAN layer with n in dimensional inputs and n out dimensional outputs can be defined as a matrix of 1D functions. So we have this matrix phi, which has all the 1D functions that we need to learn to be able to go from one layer to the next. So that is going to be the CAN layer that we are going to learn. And if there are NL nodes in the Lth layer and NL+1 nodes in the L+1th layer, we're going to need NL cross NL+1 activation functions that we need to be learning. Just like here. So there are 2 nodes in this layer and there are 5 nodes in this layer. So we need to learn 2 cross 5, 10 activation functions to propagate to the next layer. And the activation value of the L+1, jth neuron is simply the sum of all the incoming post activations. So L+1 the layer, j. So the first neuron in the second layer is going to receive all the activation functions from each feature. So it's going to receive the first input activated and then the second input activated, and then we're just going to sum that at the first node of the second layer. And all right, so x, which is what's given here. So xl+1, j is going to be the summation of the pre-activated xlji, which are these lines. So you're gonna activate the first input and then give it to this, activate the second input, give it to this, and then sum these two. So the x tilde are the pre-sum, and then we sum them to get the output of this node. All right. So the original Kolmogorov Arnold representation, I'm gonna say Ka representation. So Ka representation would then be a 2-layer CAN. And then this is the matrix form of the equation. So we just have a whole matrix of 1D B-spline basis functions that we learn. So we're gonna multiply this x with all of these basis functions to get the output at this layer. And then we just keep going. So we have phi0 of x and then phi1 of phi0 of x up to the last layer. and then we finally have the output. And now this phi is each of these activation functions are being represented using w times v of x plus line of x. Now this includes a basis function b of x, which is similar to residual connections, such that the activation function is the sum of the basis function and the spline function, spline of x. The spline of x is parameterized as a linear combination of b splines. So, which is this linear combination of b splines, and then this basis function is a Silu function, a sigmoid linear unit, which is x by 1 plus e4 minus x. And now for initialization, each activation function is initialized to have spline of x approximately 0, and w is initialized according to Xavier initialization. And then we just use backpropagation to update these spline grids with each step of training. This is how the model trains. All right, so looking at parameter count, assuming a network of depth L, layers of equal width n, with each spline of order k on g intervals. So a grid with g intervals has g plus k b-spline basis functions. Now, for this activation function, if it's a summation of all the basis functions, if g is equal to phi and k is equal to 3, which is the order of the spline function, we have a summation over 8 b-spline basis functions to get the activation function. And each of these is going to be, we're going to need n cross n. So if it's a width of n, we're going to need n cross n number of activation functions multiplied by the number of b-spline basis functions, and then multiplied by depth L. So you're going to get n square L g plus k as your parameter count, which is approximately O of n square Lg. Comparing to an MLP of depth L and width n, it would just be n square L. Now, it appears that an MLP might be more efficient than a CAN, but then the authors claim that CANs usually require much smaller n than MLPs, which not only saves parameters but also achieves better generalization and facilitates interpretability. While the two-layer with 2n+1 representation may be non-smooth, deeper and wider representations may bring the advantage of smooth activation functions. So the authors, while still assuming smoothness, allow the representations to be arbitrarily wide and deep. Now, the activations depend on a finite set of grid points G. The authors state that as long as the approximation theory in K representation holds, CANs with a finite grid size can approximate the function well within a residue rate independent of dimension. So we no longer have the curse of dimensionality. And then the authors also determined that CANs have faster scaling laws, neural scaling laws, with an alpha equal to 4, while MLPs have problems even saturating at slower bounds such as alpha equal to 1. And then the authors use grid extension to improve the accuracy of CANs. So a spline can be made arbitrarily accurate to a target function, as the grid can be made arbitrarily fine-grained. So you just increase the number of grid intervals to allow for more basis functions, allowing for more local fine-tuning of the b-spline basis functions that we learn, allowing us to be more accurate. But then, of course, we run into the problem of overfitting. And then grid extension can be performed for all splines in a CAN independently. So one can first train a CAN with fewer parameters and then extend it to a CAN with more parameters by simply making its spline grids finer without needing to retrain the model. Right, so this is a sample training curve on a toy example. The number of grid points starts at 3, increases to a higher value every 200 steps. So the optimizer used is LB-FGS, which the authors claim to be performing well for a CAN. So at the end we end up with 1,000 grid points, and we can see how every time we perform fine graining, the training loss drops faster than before. And however, the test loss first go down and then go up, displaying a U-shape due to the bias variance trade-off. It is observed that optimal test loss is achieved at the interpolation threshold, around when the number of parameters match the number of data points. So Okay, and then they also train, so this was tested on 251 CAN, and then they also train at 211 CAN on the data. Interestingly, this model achieves a lower test loss than 251 CAN with clearer stack case structures, and the interpolation threshold is delayed to a larger grid size as a result of fewer parameters. So the authors state that smaller CANs generalize better and propose methods to auto-discover such minimal CANs. And this is a plot of test loss versus grid size. So it's scaling at g power minus 3, which is not the estimated alpha of 4, but it is still better than MLPs. And additionally, we can see how training time compares to the grid size. So training time scales favorably, which can be seen in this graph when we increase the grid size. All right. So CANs can be visualized in a way that is interpretable for humans. And when the symbolic formula is unknown, or if there's no direct symbolic relationship, we can now determine how to choose the CAN shape that best matches the structure of the dataset. So the authors propose to start with a large enough CAN, train it with the sparsity regularization, and then prune it to get a minimal symbolic representation. Now for regularization, they find that L1 is insufficient, and so they add an additional entropy regularization term. So this is the L1 regularization term, which is this, and then we have the entropy regularization term across all layers, which is this. And then so the model is first trained with regularization, and then based on transparency we see which is most significant, and then we prune the model based on significance of feature, and then we try to identify, if you're able to visually see that, say this is a sine function, we fix it as a sine function. Else we use an automatic method to try to find out the symbolic relationship, and then we set it to that. So this is set to a squared, this is set to an exponential, and then now though these symbolic functions are set, they still need to be either translated or scaled. So there are some affine parameters that still need to be trained to bring the traditional sign to whatever was learned here. So we train these affine parameters to reach the machine precision, which was reached here. We try to bring it back to this point, so that now we know what exact relationship exists between this feature. So this feature would now have to be passed through this specific sign. So a sign of 3.14x plus y square, and then exponential of this value is going to be our output. So we kind of determine the symbolic relationship between the output and your inputs x and y here. So we determine that the f of x comma y is e power y square plus sine of pi x. If there's a symbolic relationship that exists, we are able to get to this. If it does not exist, we are able to get to an approximation of this relationship. Or we could simply, this is if we do need a symbolic relationship that needs to be identified. If we don't need to identify a specific relationship in terms of these formulas, we can just learn the method and learn the model here and use this itself for either regression or classification. All right, so the authors perform a number of experiments and case studies on using the CAN. So they test data fitting. They see that CANs show superior performance at fitting complex data sets. A 2-layer CAN can achieve better accuracy with fewer parameters than a 4-layer MLP. And then we already saw how for PD solving, CANs achieved mean square error much lower, 10 power minus 7, compared to MLPs, which is 10 power minus 5, with much fewer parameters. And then they took up a few toy datasets. They constructed 5 examples which had smooth K representations. And then they trained again by increasing grid points every 200 steps, and then compared it with MLPs with different depths and widths. So they saw that CANs have better scaling curves. And so this is actually the plots for the 5 toy datasets. You can see how the blue line, which is the CAN, was able to get better scaling curves compared to the MLPs. And then in the last example, they compared two cans of both depth 3 and depth 2. The blue line is depth 3, and we can see how deeper cans seem to have better expressive power sometimes. And they also try to find the approximate K representations of special functions for which we do not know the shape. Some auto-discovered cans had compact shapes which can save a lot of memory. When you train with regularization and then prune it, we're able to discover automatically the symbolic relationship, which might be simpler, but then a little less interpretable. So they also compared human constructed cans and auto-discovered cans by pruning on the multivariate equations from Feynman textbooks. They saw how auto-discovered cans were smaller than human constructed ones at a cost of interpretability. Testing PD solving using cans, they observed that cans had much better scaling laws, smaller error, smaller network, and fewer parameters. So they also tested in simple examples of continual learning by passing 5 Gaussian peaks at different phases. They observed that the CAN was able to learn the representation, whereas an MLP did not. So CANs have local plasticity, and leveraging the locality of splines, we can avoid catastrophic forgetting. So a sample will only affect a few nearby spline coefficients and leave the faraway coefficients intact. So this was validated by this example, and we can see how there is potential for continual learning using CANs. So a couple case studies are also taken up testing using CANs for discovering physical and mathematical laws, such as knot theory and Anderson localization. So in knot theory, applications were studied both in supervised and unsupervised methods. In supervised, CANs achieved better accuracy than MLPs in the signature classification problem with much fewer parameters, which can be seen here. They were able to get 81.6% accuracy with just 200 parameters, whereas DeepMind's MLP was able to get 78% accuracy with 3 into 10 power 5 parameters. And then in an unsupervised structure, it was able to uncover complex relationships in structures. And then Anderson localization, so CANs were also seen to help in modeling and understanding this phenomenon in condensed matter physics. They provided insights that align with the known physical laws and offer new perspectives as well. All right, so looking at how the paper contributes to the previous works and adds on to them. So we saw how K representations have previously been used to build neural networks, but then the paper contributes to this by making the model generalizable by going beyond the original 2-layer with 2n+1 representation that the theorem provides, and making use of backpropagation for training and increasing the expressive power of these models. So the paper defines what a CAN layer could be, and it allows us to build Kolmogorov Arnold networks of arbitrary widths and depths, allowing us to build deeper networks that are able to learn complex relationships, while also being able to learn univariate functions. With respect to neural scaling laws, the paper shows that a high-dimensional function can be scaled as a 1D function if it has a smooth K representation. So this is an alpha equal to 4 is a very high, it's a very fast scaling exponent, but then this was only achieved on synthetic data sets. So it still needs to be tested. Mechanistic interpretability is aiming to understand the inner workings of neural networks. It's either active or passive. Active MI research attempts to achieve interpretability by designing intrinsically interpretable architectures or developing training methods to explicitly encourage interpretability. So the author's work lies in this category, where the model and training methods are by design interpretable. Learnable activations is something that has already been worked on as well. Many people have studied learning activation in a differentiable way or searched in a discrete way. Activation functions are parameterized as polynomials, splines, sigma linear unit, or even neural networks. So CANs use B-splines to parameterize the activation functions. So this is the contribution with respect to this. And so CANs are very similar to neural network-based symbolic regression methods, But then they differ from previous works in that these activation functions are continuously learned before symbolic snapping, rather than manually fixed by the user. And so the authors also demonstrate that CANs can replace the paradigm of using MLPs for PD solving, and there's potential to replace MLPs with CANs in even the physics-informed neural networks and all the other networks that are generally used. Actually, there's already been a lot of work with respect to using CANs with, convolutional networks. There's already a paper on temporal CAN, which uses CANs for RNNs and LSTMs. There's also a lot of repos being released with using it for LLMs, with transformers and all that. So it's pretty promising work. Right, that is the end of the presentation. Thank you.